newer topic. Yeah, it just uses the things that you already know about, orthogonality and eigenvectors. Okay, so this is called a spectral decomposition theorem. So yeah, so so you know what a symmetric matrix is? Symmetric matrix. So what is a symmetric matrix?
Aij equal to Aj
Yeah.
for all I and j.
So it's a square matrix first of all. Okay, let's and you can define symmetric matrix over any vector space, but let's say we are looking at real vector spaces for now. Yeah, so square matrix first of all, such that M transpose equal to M. Right. So if you just take the interchange the rows and columns, it's the same thing. Okay. Yeah, where do you see symmetric matrices? Is symmetric matrices seen often in practice?
Yes, sir. For example, adjacency graphs of undirected graphs. Sorry, adjacency tables of undirected graphs.
Yeah, so adjacency matrices, right? Adjacency matrix of undirected graphs. Yeah, and many things are written like undirected graphs, right? For example, like a distance between cities, right? It's an undirected graph. I mean, the distance between A to B is the same as B to A. Yeah. So yeah, that is Mij equal to Mji. Okay, so we understand what a symmetric matrix is, and yeah, so these are also widely used in practice. Many matrices tend to be symmetric matrices. So it's good to understand what are the eigenvectors, eigenvalues of symmetric matrices. Yeah, can you say anything more interesting about them? Yeah. So the first interesting thing about symmetric matrices is this is the interesting theorem. It says that a symmetric matrix yeah, has real eigenvalues. Yeah. What do I mean? So yeah, we are restricting to real. Yeah, so matrices are real entries. Yeah, and we said that so does all the eigenvalues of M need to be real? So given a matrix, the eigenvalues do they need to be real?
No, sir.
Yeah, why is that?
So like polynomial might have non-real solution, the characteristic polynomial.
Yes. So a polynomial factorizes into roots only over the complex fields, right? I mean, there are polynomials like x squared plus x plus 1 which doesn't factorize into real roots. Yeah. But a polynomial always factorizes into complex roots. Yeah. And the complex roots of the characteristic polynomial are the eigenvalues. Yeah. So eigenvalues in general need not be real. Even if the matrix is real, eigenvalues can be complex. But the interesting thing about symmetric matrix is the eigenvalues of a symmetric matrix are always real. Yeah. Is the theorem clear? Any questions about the theorem statement?
So for a symmetric matrix, left and right eigenvectors are same.
Symmetric matrix left and right eigenvectors are same. That is very nice. Yeah, that's a very nice observation. Yeah. What is said is, so why is that? M times V equal to lambda times V. And so you are saying V transpose M is also eigenvector, is it? Why is that?
Sir, we get a condition, if left and right eigenvectors are same, we get a condition that det of M minus M transpose equal to 0.
Yes. So, okay. So you are saying you can observe it from the, so why is the eigenvector same? Yeah, left and right eigenvalues are the same for all matrices. That we already know. Right? Why is the eigenvector same?
Sir, I think eigenvectors are different, like dimensions are different for left and right.
No, it's an n by n matrix. Symmetric
Okay.
matrices are
Sir,
all.
for a symmetric matrix, it kind of follows from matrix multiplication. Or you
So
can
can you tell
essentially
me?
take,
Can you
you
tell
can,
me how?
sir, so in supposing I take M times V, I take the first row of M and dot product it with the entries in V, right?
Yeah.
Now, supposing I take the same V and flip it over side horizontally.
Okay.
Now I'm essentially taking the I'm taking V and dot producting it with the first column of M, which happens to be the first row of M because you've transposed it.
Yeah. Is that clear to everyone?
So could you say that once more? I didn't quite like.
Yeah.
It was too fast.
Yeah. Sure. Yeah. So this equation is basically, yeah, like this. No, you have a square matrix here. V is a column vector, and the lambda times V you get, right? This is what this equation means, right? Yeah. So what is how do you get this V? You are taking the dot product of V with the first row. You will get the V1 here, lambda times V1 here. You will take dot product of V with the second row. You will get lambda times V2 here, and so on, right?
Yes, sir.
Yeah. Now, what is M transpose? You take the first row of M and make it the first column of M. M transpose. That's what you mean by M transpose. No, you make rows equal to columns.
Sir, one doubt, sir.
Yeah.
Sir, the right eigenvector will be of dimension n cross 1 and the left will be 1 cross n, no, sir?
Yeah. So, I mean, they are the same meaning. One is the transpose of the other.
Okay, sir.
Yeah. So, how did we obtain this lambda times V? You just take the dot product of V with the rows of M. And the rows of M is nothing but columns of M transpose. You agree? The rows of M are nothing but the columns of M transpose. Now, if you do take V transpose and do the left multiplication, you are again taking dot products with the columns of M transpose, which are rows of M. Right? Any questions? Is that clear, Vivek?
Yes, sir. So we'll get V transpose as a pre-multiplication. So because we are multiplying the columns.
Yeah. So V is a left eigenvector. Is a left eigenvector with eigenvalue lambda. This is true if and only if V transpose is a right eigenvector. Do you agree with this statement?
Sir, for a symmetric matrix.
Yeah, for a symmetric matrix, of course, it's for a symmetric matrix. In today's lecture, everything is a symmetric matrix. Yeah, so for a symmetric matrix.
So, but we are writing it as mv equal to lambda v, so isn't v a right eigenvector?
Yeah, V is a right eigenvector. Sorry, I should say right eigenvector and left. Okay. But the statement is the same even if I insist in left and right, right?
Yeah.
Okay. Yeah. So this is the interesting observation, right? This was your doubt. Many of you had the doubt. What is the relationship between left and right eigenvector? So at least we have an answer for symmetric matrices. Yeah, they're essentially the same. Okay. Yeah. So okay. So what? How
Excuse me,
can we
sir.
use this? Yeah.
So, but even for a general matrix which is not symmetric, if V is a right eigenvector of M, then V transpose would be a left eigenvector for M transpose.
How do you show that? I don't know how to show that.
Just take
Sorry,
transpose on
that
both sides on the
V
equation,
transpose
sir.
is right
So-
eigenvector for M transpose. It is true, sir. But for M is not true. That's
So
what
it is for M transpose, it is in general true, sir.
Yeah, for M transpose, but I'm saying V transpose is the left eigenvector of M itself.
M, because M equal to M transpose, yes.
Yeah. Yeah, for M transpose, that's an obvious statement. Means obviously, if you transpose everything, then the eigenvector. Yeah, but here the same matrix, the left and the right eigenvector, there's a connection. Yeah. Okay. So what can we do with it? Yeah. So let's take. So let V be a eigenvector. Yeah, with eigenvalue lambda. So let's look at V transpose MV. Yeah, and let's do one more thing. So the eigenvector V might have complex entries. Okay, the eigenvalues is real. That doesn't mean the eigenvectors are. Sorry. So we need to. Yeah. So right now we don't know this statement of the theorem is true. Okay. So lambda might be complex. V can also be complex. Yeah. Yeah, so lambda and V can be complex as of now. Okay. So let's look at V bar M.
So
Yeah.
even though we're taking M to be in R and cross N, we are considering V can have complex values. Is that it?
Yeah. So this is we discussed a lot previously. No? Okay. Could you mute yourself? There is some background noise. Yeah. So M is a real matrix. Yeah. But it's also a matrix over complex field, right? Yeah. And over the complex field, it has eigenvectors and eigenvalues. Yeah. So the vectors, eigenvectors might have complex entries and the eigenvalues might be complex. Yeah. But we want to show that if it's symmetric, then it has real eigenvalues. Okay. So as of now, we don't know this theorem is true. Yeah. So in general, these are complex. So let's look at this particular quantity. What is this particular quantity? What's the dimension of this particular quantity?
Sir, what is V bar there?
V bar is complex conjugate.
Sir, 1 cross 1 scalar number.
Yeah, so this is a scalar value. It's a 1 cross 1 matrix or a scalar value. Right? So let me now expand it in two different ways. Yeah. So what is this? So we can do this as this is lambda times V. Yeah. This is going to be lambda times V bar transpose V. Right. And what is this quantity?
Dot product of V with itself.
Yeah. This is the complex dot product. Yeah. So you also taking the conjugate also. Yeah. So this is the dot product of this is the inner product of V with itself over the complex numbers. Yeah. Now let's do it the other way. Okay. So now what should I do? Any ideas?
The V bar transpose is also an eigenvalue, so we can replace with lambda times V bar transpose.
Okay, so you are saying this can be replaced by the so okay, but why is V bar transpose an eigenvector? It is V bar, no? V have complex entries, no?
Sir, if A and B are two complex numbers, then conjugate of A plus B is equal to conjugate of A and plus conjugate of B. So
What are you suggesting to write here?
I'm suggesting, like, since the entries of the vector obtained are simply linear combinations of the original coordinates of the original vector, the conjugate of the whole will remain the conjugate of the new vector. So I'm essentially saying V conjugate will still be an eigenvector.
I'm not sure. Why is V conjugate? If V is eigenvector, you are saying V conjugate is also eigenvector, is it?
I think so.
I'm not
Yes,
sure.
that is true for polynomial with real coefficients.
Oh, I see. So you are saying m times V equal to lambda times V implies that m times V bar, yeah, equal to lambda bar times V bar. Is that what you are saying? Is this what you are saying?
Yes, sir.
Okay. Is this true for any matrix?
So we have M to be in R n cross n.
M to be n cross n. Okay. So why is this true? So this is true only for real matrix. Okay. M is a real matrix, then this is true. Is that what you are saying?
Yes, sir.
Yeah. Does everybody agree?
No, sir. I don't. I have a doubt. Like I didn't quite understand how this came out.
Okay. So I mean, I can take conjugate on both sides.
Yes, sir.
Yeah, I take conjugate on both sides. So what do you mean by conjugate of a matrix? You do the conjugate for every entry in the matrix.
Yes, sir.
Yeah. Conjugate of a vector, you do the conjugate for every entry in the vector. So the thing is, M is a real matrix, right?
Right. So the conjugate of each entry is actually the entry itself. So it's M itself.
M itself. Yeah.
Okay,
We can have complex values, so the V bar is still there.
Right, sir.
Yeah.
So we can find another approach, like we can split the matrix V into real and complex parts.
But the matrix is only real.
Sir, the matrix V, sir. I mean, we
Okay,
can split
V.
vector matrix.
Yeah, sure,
Real
sure.
V and complex V.
Yeah. So, but this statement, you are saying how to prove the statement?
Yes, sir.
Yeah. So, I mean, this is just a complex. So, the entries in entries here is basically linear combinations of the entries here, and like a complex. So, if you have a linear equation, if you take the complex conjugate on both sides, that's also equally true, right? Because this complex conjugate goes over additions, multiplications, and everything, right? So A plus B, the whole bar is A bar plus B bar, right?
Yes.
You agree?
Yes, sir.
This is also true, right? Is this true? Is this true? Complex numbers, come on. You guys
Yes, sir.
just finished the entrance and everything, right?
Yeah, it's true.
Yeah. So from these two, you can conclude that this is also true. Right?
Sir, why is it necessary that M be real?
No. In today's class, we are looking at real symmetric matrices only.
Okay, sir. Okay.
Okay. Yeah. today's class we are talking about real symmetric matrices only. Yeah, we can ask what happens to other matrices, that we will ask later for now. Okay, fine. So now what should I write here? What should I write here?
Sir, instead of M, we should M transpose.
I should write what?
M V bar whole transpose in the bracket.
Okay, so but what was suggested was a simpler thing, no? So look, yeah, so you can write M V bar the whole transpose times V. Okay, so this is lambda bar times V bar, right? This is lambda bar times V dot V. You agree? Yeah, so now what can we conclude?
Sir, we have lambda equal to lambda bar.
Lambda equal to lambda bar.
Sir, there's a transpose missing in the last but one equation.
Oh, you are saying, so here's a transpose here.
Yes.
Yeah. So from this is 1, this is 2, from 1 comma 2. And what does this mean? Lambda equal to lambda bar.
Lambda is a real number.
Yeah, implies lambda is a real number. Yeah. So if a symmetric matrix, yeah, I mean any eigenvalue of a symmetric matrix has to be real. Yeah, the eigenvector might be complex and everything, but the eigenvalue always has to be a real number for a symmetric matrix. Okay. Is this clear?
Sir, could you explain why V bar transpose into V is dot product of V?
So this is what we defined as the dot product for the complex case. I mean, in a complex vector spaces, V bar. So this basically is the inner product. This is how the inner dot product is defined for complex. Yeah.
Yeah.
This is covered in class. If you go back to previous lectures.
Okay.
Otherwise, it's not a dot product. If you simply take your normal dot product, this is not a dot product in complex vector space. Okay, because yeah, your norm might become complex valued. The complex yeah, norm has always to be a real valued, positive real valued number. Yeah, the only way to make it is you have to make a conjugate here. This is the definition of dot product in a complex vector space. Yeah.
Yeah. Okay, sir. Good.
Yeah, and yeah, so and remember V is a non-zero vector. I mean, yeah, this can also be equal if V is a zero vector, but V is a non-zero vector because eigenvectors are non-zero. Okay, yeah. So we saw something interesting about symmetric matrices, right? The eigenvalues are real. Very nice. Yeah. So another interesting theorem about them is if V comma W has distinct eigenvalues, say lambda 1 and lambda 2. Yeah. Then V dot V comma W are orthogonal. Yeah. So if you have eigenvectors with different eigenvalues, they have to be orthogonal for a symmetric matrix.
Sir.
Yeah.
Orthogonal with respect to which product, which inner product?
The typical, the normal dot product, that is V bar transpose W equal to 0.
Okay, sir.
So in today's class, we are talking about a square symmetric matrices with real entries. Okay, and our dot product is basically this. Yeah, your vectors can be complex, and your dot product is this. This means this. Okay, so how do you prove it? Any suggestions? So let's write down what we know. What do we know?
M times V equal to lambda 1 times V.
Yeah, m times V equal to lambda 1 times V, and m times W equal to lambda 2 times W. Okay, so now what should I do? Yeah, so let's try to do something like this. Yeah, so some trick like this we can do. So here what we did, we looked at this. Yeah, we grouped things separately. Yeah, so what should I write?
W bar whole transpose MV.
W bar whole transpose MV. This is what kind of value, this quantity?
1 by 1 matrix, which
So
is
1 by 1 matrix. Okay. So now let's try to group things in the left side and see what happens. Yeah, so what should I write now?
MV is lambda 1 into V.
Yeah, so lambda 1 into V. So in the end, this will become
Dot product of W and V.
okay, good. Okay. Now let's group it the other way. Yeah. So what should I write? So we are grouping it this way now. So what happens?
Lambda 2 into W whole transpose. Lambda W bar whole.
Lambda 2 into W bar the whole transpose times V. Everybody agrees?
Sir, lambda 2 bar.
Lambda 2 bar. Okay, lambda 2 bar. It's lambda 2 bar, right? Yeah, just a second. Yeah, but we already proved that the eigenvalues of a symmetric matrix are real, right?
Yes, sir.
Yeah, so lambda 2 bar is?
So lambda 2 bar is lambda from previous result.
Yeah,
Now
from the
lambda
previous result.
and lambda 2 are equal, but it is a contradiction because lambda 2 and lambda 1 are given distinct.
No. So what does these two imply? This is equation 1, this is equation 2. Yeah.
Lambda 1 equal to lambda 2.
Why does it say lambda 1 equal
sir,
to?
unless the dot product of W and V is 0.
Yeah, so this means that lambda 1 minus lambda 2 times the inner product of W and V equal to 0. That's what this means, right?
Yes, sir.
Yeah. This is these are distinct. Okay, it's clearly written. These are distinct. So this is not equal to 0. Yeah. So this implies that the inner product of W and V has to be equal to 0. You agree?
Yes, sir. Hence they are orthogonal.
Hence they are orthogonal. Yeah. So yeah. So what did we do? We just wrote down what we know and just to work things out. Yeah. I mean, we are talking about orthogonality, so it's natural to consider this particular thing. Yeah. Okay. Questions?
Sir, since the eigenvalues are real, this should also imply that like the eigenvectors have real entries in it.
Why is that? Why do you say so?
Because we then simply, if lambda is real, then we simply get homogeneous equations in real entry. Then we solve it, then we should get real entries in eigenvectors too, right?
But why should this have a solution always? This need not have a solution for any lambda. You are saying keep V as unknowns and solve this equation, right?
Yeah.
Yeah. So this yeah, but why should this equation have a solution over reals? Maybe that equation doesn't have a solution.
So how will it not have, like, should have a solution?
Why should why should it always have a solution? Just a second. Yeah, why should it always have a solution? I'm not sure.
So if we simply like take it on the other side, we can write it as m minus lambda 1 into v, and then we get like n linear equations.
Yeah, why should that be? So M is a full rank matrix. You can assume that M is a full rank matrix. It is invertible. Yeah. But still, why should this have a solution?
Okay.
If M is a full rank matrix, then Mx equal to B has a solution. I agree with you. Yeah. But this equation is not of the form Mx equal to B.
Yes, sir.
Yeah. So it's unclear. Yeah. I mean, we can have complex values. Yeah. Yeah. So how do we know that there is a solution V over complex numbers? That is because from the characteristic equation we found that lambda 1 is a eigenvalue. Yeah. If lambda 1 is a eigenvalue, we know that there exists a eigenvector with that particular eigenvalue. This we derived previously. Yeah. If every root of the characteristic equation is a eigenvalue and there is a eigenvector, non-zero eigenvector corresponding to it. Yeah, this we covered in class. Okay. If you have a doubt, you can ask me later and I can tell you the proof again.
Yes, sir.
Yeah. Okay, so this is very nice. Okay, so symmetric matrix looks like they are very special. Yeah? They have real eigenvalues. Yeah, and distinct eigenvalues. They are orthogonal. The eigenvectors are orthogonal. Yeah, very nice. Yeah. So there is one more interesting result, yeah, which kind of is follows from kind of these two things. Yeah. So so how do you diagonalize a symmetric matrix? Is a symmetric matrix just diagonalizable? What do you think? What can we say about diagonalization of symmetric matrices? Are all symmetric matrices diagonalizable?
They should be all diagonalizable because we are having n unique eigenvectors, and I mean eigenvalues whose eigenvectors are all orthogonal to each other. So they are all forming orthonormal, like they can form an
All the
orthonormal manner.
eigenvalues be distinct. Why should all the eigenvalues be distinct? I mean, if I agree, if there are n distinct eigenvalues, yeah, then what you are saying is true. But that is nothing specific to symmetric matrices. No, there are n distinct eigenvalues. Then there are n orthogonal, sorry, n linearly independent eigenvectors also, right?
Yes, sir.
Yeah. So okay, the interesting thing for symmetric matrices is if you have n distinct eigenvalues, then not only you have n distinct eigenvectors, but they are also orthogonal. Yeah. For symmetric matrices, yeah, if there are n distinct eigenvalues then there is a basis of orthonormal eigenvectors. You agree?
Yes, sir.
Yeah. So earlier, we had a basis of eigenvectors, but for symmetric matrices, the interesting thing is you have a basis of orthonormal eigenvectors.
You say orthonormal or orthogonal?
If you have orthogonal eigenvectors, you can make it orthonormal also by just dividing by the norm.
Yeah.
If you just divide by the norm, the eigen, it still is an eigenvector, no?
Yes, yes.
Yeah. Okay. Yeah. Everybody agrees with the statement?
Sir, what does the span of this set of vectors produce?
It's a basis, so it's the entire n-dimensional vector space.
Entire n-dimensional vector space.
Yeah, that's what a basis means, no? So you have n distinct eigenvalues. That is, there are n distinct eigenvectors, and these eigenvectors are orthogonal. We already proved here. You agree?
Yes, sir.
Yeah. So there should be, so there are n vectors which are linearly independent. So they have to be a basis for the whole space, right?
Yes, sir.
Yeah. Narahari Shetty, is it fine?
Yes, sir.
Yeah. Okay. But the interesting thing is, we will just we'll now show that this particular thing is not needed. Yeah, this particular theorem is true. Yeah, you don't need to have n distinct eigenvalues. For a symmetric matrix, there is a basis of orthonormal eigenvectors. Okay, so this is the theorem we want to prove. Is the statement clear? Questions? Okay, so how do we show this? Yeah, we want to show that for any symmetric matrix, yeah, maybe there are not distinct eigenvalues, yeah, but still, yeah, there is a basis of orthonormal eigenvectors, yeah, and actually, this is a if and only if. Okay, so this you can write if and only if, yeah. It's very easy to see that. So let's show one direction first, yeah. So what is the reverse direction? If there, so suppose you have a basis of orthonormal eigenvectors, yeah, is the matrix symmetric? Yeah, so can we prove the reverse direction? How do you prove the reverse direction? No ideas? Reverse direction should be very easy. So suppose there is a basis of orthonormal eigenvectors. Suppose there is a basis of.
So in that case, we get a diagonal matrix which is always symmetric.
Okay, is that good enough? But then you can say it for I mean, any matrix. No, where have you used the fact that it's a symmetric matrix?
Sir, I am talking about the case like if there is a basis of orthonormal eigenvectors, then it is symmetric.
Why is that?
Because we can represent the transformation as a diagonal matrix directly.
So M is not a diagonal matrix. M is a matrix which has a orthonormal basis of eigenvectors. So what should I do from here? So what does the diagonalization theorem says? If there is a basis of eigenvectors, what does the diagonalization theorem says?
Say P inverse times M times P is a diagonal matrix.
Okay, so I mean, if you have a question, it's better you speak out. Okay, in the chat, I cannot always look at the chat. What is the reverse statement? Yeah, so this is a if and only if. That is, this is true. You have a symmetric matrix if and only if there is a basis of orthonormal eigenvectors. Yeah, so to prove the statement, there are two statements we need to prove. If you have a symmetric matrix sum, then there is a orthonormal basis of eigenvectors. The reverse statement is, if you have a matrix sum with the orthonormal basis of eigenvectors, yeah, then it's a symmetric matrix. Is that clear?
Yes, sir.
Yeah. So now we are assuming that you have a matrix M, yeah, which has a orthonormal basis of eigenvectors. Yeah. Now what does exactly does that mean? Yeah. Then we can diagonalize some, right? It's a basis of eigenvectors, so we can diagonalize some. M is diagonalizable. Yeah. So what does that mean?
So there exists a matrix P such that P inverse MP is equal to a diagonal matrix.
Everybody agrees? Yeah. Now the interesting thing is we also need to use the fact that this basis is orthonormal. Yeah. So what can we say about P if this basis is actually orthonormal? So if you look at this P matrix, this is a change of basis matrix, right? Yeah. So since this is not just a basis of eigenvectors, it's the basis of orthonormal eigenvectors. That means the columns of P, yeah, are orthonormal. You agree?
So I didn't quite understand that.
So I mean, this P inverse MP, for getting this P inverse MP, you just need a basis of eigenvectors, right?
Yes, sir.
Yeah. But we not just have a basis of eigenvectors, we have a basis of orthonormal eigenvectors.
Yes, sir.
Yeah. So the change of basis transformation you are doing, say you are changing from one orthonormal basis to another orthonormal basis, right?
Yes, sir.
So then the change of basis matrix, the columns of that matrix has to be, I mean, orthonormal.
Yes, sir, because it is the
Yeah. If you are changing a basis from an orthonormal basis, which is standard basis, to another orthonormal basis, the change of basis matrix has to be, the columns as well as the rows of that matrix has to be orthonormal. Yeah.
Yes, sir.
Yeah. So P. So what is P inverse actually?
P transpose.
P inverse is nothing but P transpose. Yeah. So P transpose times P is basically taking the, dot product of the columns of P with itself, with among each other, and this is actually identity. Yeah. Yeah. So this statement actually says that P transpose MP is the diagonal. You agree? Yeah. So now what can you say about P? So what is sum? M is basically yeah, P D P transpose. Do you agree? Is this correct?
And transpose is also same.
Is this correct?
Yes, sir.
And then what is M transpose?
PDP transpose.
Implies that M is symmetric. Is that clear to everyone? Yeah.
Yes.
Yes, sir.
Hmm?
Yes, sir.
Yeah. So if we assume that the matrix M has a basis of orthonormal eigenvectors, yeah, then M has to be a symmetric matrix. Yeah. Then M has to be a symmetric matrix. Yeah. So this is the backward direction of the statement, and we need to prove the forward direction of the statement. Yeah. That is, you are given a symmetric matrix. Yeah? Can we find a basis of orthonormal eigenvectors? Okay, so we are given that M transpose equal to M. Yeah, and we need to find a basis of orthonormal eigenvectors. Yeah, is the plan clear? What we need to do?
So for that, first we have to prove if M is symmetric, then it is definitely diagonalizable.
Yeah, if M is symmetric, is it? Yeah, if M is symmetric, is it always diagonalizable? Yeah, that we need to prove. That is also an important thing we need to prove for proving this thing. Yeah, you are right. Yeah. So, okay, so any matrix, yeah, has at least one eigenvector. So this is a statement. I mean, yeah, I don't know if we proved it in class. Yeah, this might be something I'll give you as a exercise to work out. Yeah, so any matrix, yeah, has at least one eigenvector and one eigenvalue. So at least one eigenvalue. Yeah. So if you take a matrix, it should have at least one eigenvalue. Okay. Yeah. So this is a theorem that I haven't proved. Yeah, but you should just believe me right now. Okay. Any matrix has at least one eigenvalue. So we can assume that M has one eigenvalue lambda, right? So there exists V comma lambda such that M times V equal to lambda times V. Okay.
Sir, there is an eigenvalue doesn't necessarily mean that there is an eigenvector with the same eigenvalue.
Now if you have an eigenvalue, it should come with some eigenvector also, no? How can you have an eigenvalue without an eigenvector?
Sir, when geometric multiplicity is 0 and algebraic multiplicity is something.
Geometric multiplicity is how can geometric multiplicity be equal to 0? No, if lambda is an eigenvalue, then geometric multiplicity has to be a non-zero number, no?
So
Lambda is a, so what is the definition of eigenvalue? Yeah, if lambda is an eigenvalue, then there exists V not equal to 0 such that M times V equal to lambda times V. This is the definition of eigenvalue. Right? The definition of eigenvalue is there should be a non-zero vector such that m times v equal to lambda times v, right? Sri Harsha, is that clear?
Yes, sir. But we just assumed that there exists a vector, but
But
in
that's the
reality,
definition of eigenvector. I mean, that's the definition of eigenvalue. You should have an. This equation is always true for the zero vector. This equation is always true, no matter what lambda is. This equation is always true for the zero vector. You agree?
yes, sir.
Yeah. So then every real number is an eigenvalue if we include zero vectors also as eigenvectors. Yeah.
Yes, sir.
So the only way this makes sense, the definition of eigenvalue makes sense is you have a non-zero vector, yeah, with eigenvalue lambda, for which this equation is true. Yeah. So when you say there is one eigenvalue, then there is also one non-zero eigenvector. Okay.
Sir, I have a question. Can I ask?
Yeah, please.
Sir, in that statement, any matrix has at least one eigenvalue. Is there any constraint on the matrix or the eigenvalue? Because if not, can't we just say for every matrix, the characteristic polynomial will have at least one root in the complex plane, so it will always have one eigenvalue, minimum.
Yeah, it will mean. Yeah. So I mean, that's right. I think essentially that's the whole thing. Yeah? So you have the characteristic vector. There has to be at least one root for the characteristic polynomial, right? It might be some x minus lambda whole raised to n. Yeah.
Yes, as long as you consider it in the complex plane, you should be fine, right? Because everything has a root in the complex plane. So.
Good. So you have proved the statement now.
I think so. As long as there's no constraint there, it should be fine, right?
Yeah. So that's essentially the proof of the statement. Yeah. So yeah, I mean, so every matrix has to have at least one eigenvalue. Okay. Thanks. Okay. So you have something like this. Yeah. Now, so you have one eigenvector also you found. Yeah. But it's possible that the geometric multiplicity of this lambda might be equal to 1. It could be possible. The geometric multiplicity could be equal to 1. Yeah. And the algebraic multiplicity could be equal to n. Yeah. But geometric multiplicity could be equal to 1, and algebraic.
So, but if we consider the complex plane, then any matrix will have all the n eigenvalues, right?
But all of the eigenvalues could be the same, no? All of the eigenvalues could be the same, no?
Yes, sir. But okay, then it will be has at least one eigenvalue. Yes.
Yeah, that's what is written.
Sir, but there should be a constraint now, right? Because M is a symmetric matrix and it always has real eigenvalues. So there should be a constraint on eigenvalue being real number. We can't just consider it an complex plane, right?
So we showed that if it has an eigenvalue, it has to be a real eigenvalue. Yeah. So I'm just saying so we haven't used the fact that M is a symmetric matrix for making the statement. That's what you are saying.
Yes.
Yeah.
So that very soon. Constraints, right? Like I thought this was not for a symmetric matrix because the statement says any matrix. So as long as you take any matrix without any constraints, it should be true.
Yes. Yeah. So I agree with Shyam. Jignesh, that we haven't used the fact that M is a symmetric matrix yet. Yeah. So we are going to use that. So now let's take a orthonormal basis for the vector space. So let's say we have an orthonormal basis which is V1. So let's say W1 to Wn. say orthonormal basis for the vector space for r raised to n, yeah, such that we will start making our orthonormal basis w1 equal to v. Okay. Yeah, so our w1 equal to v. Now let's change the basis to orthonormal basis. Okay, so let's change the basis to the orthonormal basis. Yeah, so let's do this P inverse MP we are doing. Yeah, and this is equal to P transpose MP, right? We are changing orthonormal basis, so we are doing this. Yeah, is that clear? Now, so what is happening here? So we are basically doing this 3 matrix multiplications. Yeah. So yeah. So remember that okay, we are almost out of time today. Yeah. So I think I'll cover this theorem in the next lecture. Okay. We will show that this particular matrix that you get, yeah, has to be a symmetric matrix. Okay. So sorry, you will actually have some recursive argument. Yeah. So we will show that. I mean, if you do this, yeah, you will. Yeah. So I mean, I need some time to discuss that. Okay, so let's cover this particular theorem in the next lecture. Okay, so what did we do today? Yeah, so we were interested in symmetric matrices, symmetric real matrices. Yeah, and the first interesting thing about symmetric matrices, symmetric matrix has always have real eigenvalues. Yeah, all the eigenvalues of a symmetric matrix are real. Then we said that if you have eigenvectors with distinct eigenvalues lambda 1 and lambda 2, yeah, then the eigenvectors has to be orthogonal. The eigenvalues are distinct, then the eigenvectors has to be orthogonal. Yeah. And then finally we said that if you have a basis of orthonormal eigenvectors, yeah, then the matrix has to be symmetric. Okay. And in the next lecture, we will prove the converse. That is, you have a symmetric matrix, there is a basis of orthonormal eigenvectors. Yes.
Sir, I have a doubt. Mean in the last page means the proof of this first part only. We write M transpose equals to P D P transpose ka whole transpose. On the next page.
Yeah. So this page. So yeah. Okay.
No, sir, on the previous page where it is written M transpose equals to PD P transpose ka whole transpose is equals to PD P transpose.
Okay.
So there shouldn't be D transpose also.
Okay. So what is the transpose of a diagonal matrix?
Okay, sir. Same.
Yeah. So this, yeah, the other direction, which is the hard part, we will show in the next lecture. So the class is over. You can ask questions.
Sir, I didn't get why in this proof P inverse is equal to P transpose.
Why is the columns of P are orthonormal. Do you agree?
Okay. Yeah.
Yeah, because we are changing from one orthonormal basis to another orthonormal basis. So the columns of P has to be orthonormal.
Right.
Yeah. Now, if you have a matrix whose columns are orthonormal, what is P transpose P?
Oh, right. So they're orthogonal, so the dot product will be 0.
Yeah. Yeah.
Okay.
Only the diagonal entries will become 1 and everything else becomes 0.
Okay. Got it, sir.
And that's why this is true. Yeah.
Yeah.
So if this is true, then P transpose has to be equal to P inverse.
Yeah. Got it, sir.
Yeah. Yeah. So these are, I mean, yeah, first time you see, okay, you might say, okay, why is this true? But yeah, these things, yeah, you should get used to it. Like if it's orthonormal, then P transpose equal to P inverse. Okay, any other questions? Okay, looks like there's no other questions. Okay, so okay, thank you then. Bye for now.
Thank you, sir.
Thank you, sir.
Thank you.